Section 21.3, magnetic force. Two objectives. First, we're going to determine the force of a magnetic field or its strength. And then second, we're going to look at the direction of a charged particle that's moving through a magnetic field. Who has heard of a particle accelerator before? Anybody want to explain what it is? Anybody have an idea as to what a particle accelerator is and what it does?
But they collide to atoms together.
Yeah, it's something that gets protons, electrons, small particles moving at high velocities to create collisions, to see what comes from them, to break them down further. Anybody want to take a stab at how it works or know how it works? Nick?
Yeah, these magnetic tubes that span like light miles, they keep accelerating particles around it multiple times, so finally they change their trajectory so they collide at high speeds.
Yeah, so it's magnetically induced. Very good, Nick. It's a magnetic field that gets the particles, don't start unwinding that, that gets the particles moving really fast, and eventually they will end up colliding with each other, but the goal is to get it moving. So we're going to talk about how they get moving today, really. All right? Hadron Collider, particle accelerators.
Yeah.
We just spoke for like... What? No, not a centrifuge. The blood that separates it to different thicknesses. That is cool. Can somebody read for us, please? Nice and loud. Awesome, Bobby. Nice and loud. Thanks.
From experimentation, it is seen that a stationary charged particle does not interact with a constant magnetic field. Yet a moving charged particle does. The force experienced has a maximum value when the charge moves perpendicular to the field, decreases at other angles, and is zero when the particles move parallel to the field lines.
So what we have here is this idea. This is kind of wild to think about. If an object is stationary, even if it's charged in a magnetic field, it's not going to feel force. But if it's moving, it does feel force. The motion is what kind of acts as a catalyst to a force being felt by that particle. So what does this make you think of? Think back to the beginning of the year. When an object is stationary, it remains stationary, right? Yeah, what law is that? Yeah, the inertia law, the first law. Okay, we'll say law of inertia. An object at rest will remain at rest. This is what's happening here, really. An object that's sitting still doesn't feel force. But once it starts moving, it feels a force. What does a force create? F equals? Acceleration. Very good. MA. A force creates acceleration. Thus, when an object is moving and it feels a force, it will change its velocity. So it might increase velocity, it might decrease velocity, it might just change direction and continue to curl, like we see in a particle accelerator. So we'll see that today. So this is analogous in your mind to Newton's law, except for the fact that it's really always acting under a force. Remember we said an object at rest will remain at rest, an object in motion stays in motion unless acted upon by an outside force. When it remains in motion in a magnetic field, it's due to the force, actually. So there's a little bit of a difference there, the law of inertia. But it makes you think of that, okay? Think of them analogously. Let's take a look at our formula here. The magnetic field strength is known as the magnitude of a magnetic field. That's the B value right here. That is the magnetic field strength. And it is measured in Tesla. Tesla, not the car, but the scientist.
The first X-ray.
He developed the first X-ray? You did a project on it?
No.
Oh, how do you know? You read it. That's cool. I like that. Sometimes when people know about a certain scientist, they had to do the project, right? You never did any projects on scientists when you were like in 7th grade, 8th grade? You had to do like an autobiography. Wow. I mean, about yourself. You could be a scientist, actually, but you're a little young. You had to do like a report where you read a biography on somebody and summarized it. Never?
Not on science.
Oh. Well, that's going to be an assignment for the first quarter from now on. Next year's fine. Because you know you have second quarter? We do the project with the catapult. Third quarter you did the video. Fourth quarter you do the egg drop. I'm always looking for a first quarter project. So that'll be a good way to do it then, right? So throughout the year, every time you mention a scientist, somebody in the room will have done a report on them. And I'll go through all the scientists we study in the year. I think that'd be good. Joyce, agree? It's a good suggestion, Joyce. So, the magnetic field strength is the B value measured in Tesla. That is equal to the magnetic force felt by the particle, F mag. This is the magnetic force felt by the particle. And obviously that's measured in newtons, over the product of the charge and the velocity. Charge and velocity. Coulombs and meters per second. Now, let's take a look and rearrange this formula and solve for the force. Okay, what do you get when you solve for force? Not over. Times. Okay? Magnetic field strength equals dQV. So what does that tell you? If there's no velocity, what happens to the magnetic field? Magnetic force. Magnetic force in it equals dQV.
Zero.
Yeah. If there's no velocity, what do we say about the force? The force is? Does that make sense? Look at the formula. Okay? When V equals 0, the force equals 0. What if the particle isn't charged? What if it's just my hand? Is it going to start moving? Or if it's moving, is it going to continue moving? Or feel force? No, because there's no Q. Q would be 0. It would be neutral. What if there's no magnetic field? Well, if there's no field, then there's clearly no force. If B equals 0, then F has to equal 0. But what we notice is this. The force felt is proportional to all three of those values. Again, the force felt is proportional to B, is proportional to Q, it's proportional to V, to all of them. So if the field goes up, the force goes up. If the charge on the particle goes up, the force goes up. If the velocity goes up, the force goes up. Do you see how clear that is? Okay, it's really important that you see that. You would say that they're joint proportionality. And the only reason you say that is because there's more than one parameter that is directly related to the force felt. All right, with that said, let's take a look at a right-hand rule. Yeah, right-hand rule first. So let's look at our right-hand rule. What was the right-hand rule with the current?
Yeah, if you your hand around it and towards in the direction of current, then your fingers will curl in the direction of current.
That's right. Thumb, direction of current, fingers curl in direction of magnetic field. That was for a current carrying wire. Now, let's say that a magnetic field is set up by two different charged plates, okay? And the magnetic field goes from one plate to the other in one direction. Now, with that said, our rule tells us the following. Our fingertips point in the direction of the magnetic field B. So look at the example on the board, put your fingers in that direction. That's the magnetic field. Right hand, please, everybody, let's go. Right hand, not left hand. Use your right hand, practice. You don't have to write, just put your hand in the air. Or you help us out, come on. Thank you. So, now, V stands for velocity. So V is the direction the particle is moving. So let's say that the magnetic field is up and the particle is moving into the page. Your thumb points toward the projector. So point your thumb toward the projector. I know it's tough. Do this. Okay? Like you're doing it. Oh no, you're good. Sorry. Okay, do this. Now, which way does your palm face right now? Your palm faces to the right. Try and curl your hand more. Okay? Your palm should be, yeah, you could do this actually. It's a lot easier. Sorry.
Just the thumb.
I'm going like this, like vertically. So
Yeah,
you just do that. Alright, so you can just follow that. That's not bothering like. So your palm faces the direction that the force would be felt. Think about it. If I walked up and smacked somebody on the side like that, my palm would apply force in that direction, right? That's where the force is felt. Now, we assume that's for a positive particle. If it's a negative particle, what do you think happens? Opposite direction for the force. Okay, don't start slapping each other. Please,
I'm
please.
just testing a rule.
All right, no. This doesn't work that way. So, yeah, because you're going to get a negative force in a minute this way from here. Okay, so again, positive force or force on a positive particle is out of the palm. A force on a negative particle in the opposite direction. So let's practice one of these together. All right? No, you're not slapping. So let's say that the magnetic field is acting north from where you're sitting. Which way would your fingers be pointed?
This
Which
way.
way? Up is up, down is down. Which way is north?
This way.
Guys, come on, you live in a city.
Yeah.
That way is north.
Well,
So your fingers face that way.
if I were sitting
I thought we were
this
talking
way.
about
Basics.
Oh, okay, so let me stop and pause. Here we go. Let me pause for a second. Listen carefully. This is always up.
Yeah.
Look up. Look up. Come here, look up. This is always up, this is always down. Next. This is into the page. This is out of the page. This is right. This is left. But if you live somewhere where you know your directionals, if you're given directionals, use them. So instead of into the page, this would be like north here. Okay? This would be south. This would be east. This would be west also. But here's the thing. If I'm just sitting at my desk, Mike, relax. Relax. If I'm just sitting at my desk and I'm facing this way, and I say into the page, then you're not suddenly going to be facing north. It's not always north for into the page. Into the page depends on which way you're looking, right? So if I'm reading my book and this is into the page, and this is the force or the magnetic field, and I know the velocity is left, then the force would be down. Okay? Up. This force would be left. This force would be right. So it depends on the direction you are orienting your body. Alright? Let's look at an example. We'll do an example. A proton moves straight upward. What is up? Which way is up? Point, please. Which way is up? Right? So with your thumb, the proton is moving up. So put your thumb up. Start like this. Through a uniform magnetic field that points east. Which way is east?
Left.
Right.
Oh, jeez. That's the
Okay?
next thing.
And again, that's because we know our directions here. If you're given to the right, it's the same thing as east if we're facing this way. Okay, into the page would be that way. That would also be north right now. Now, so I'm this way. Which way does my palm face? North, or if my page is here, I'm reading a page, or what is it? Into the page. Again, imagine I'm reading. Folks, do this, please. Here's the page, right? If the force is up, or if the field, if the direction is up, and the field is to the right or east, the force is into the page, or north. Mike, stop. Too giddy this morning. All right. With that said, let's write down our givens. So we know it's either north, by the way, or in this case, into the page. But when you're given east and west, you should use north and south as your answer. If you're given left or right, you should use into the page or out of the page as your answer. If you want to jot that down. North, south, east, and west stay together. So that's why we're calling this north, even though I put in parentheses. If you use up or down, if you use left or right, you can use into the page or out of the page. Okay? Don't memorize those acronyms. Now, what are our givens? What are our givens?
10, 2 times, I don't know.
The speed of 2 times 10 to the 8
Time.
Oh.
Good, so that's our velocity to start.
What is magnitude 13?
What does T stand for again?
Tesla.
So what is that variable? Good, have B. Okay, B stands for magnetic field strength, which is measured in Tesla. Next, what is my charge? What is my charge?
Oh, is that 1C?
1.6.
Yeah. Nine.
19.
16.
19. Negative 19. Negative 19. Yes.
Bobby got it. Negative 19. It's 1e, right? 1e, one elementary charge, which is this quantity. It's a proton. It's a proton. All right? Finally, we are trying to figure out what the force is. So F equals BQV. It's possible. I don't know. Remember this formula from the last slide when we solved for F. So I'm going to use this formula the way we know it. You should all be checking this answer. Let's go. On your calculator, not on your iPad. Which means I should hear some hustle and bustle.
9.6.
Thank you, Scotty. I'm putting mag for magnetic, not for magnitude. If I wanted to say magnitude, I would put a little horizontal bar over the letter F. My units are newtons, and it's acting north. So I wrote newtons north.
Oh, so the direction is part of the.
Read the question, right? The question says give the
Oh.
magnitude and direction. The magnitude, remember, is always just the number component itself.
Yeah.
So this is your magnitude right here in red, okay?
Yeah. Is that for every answer?
Yeah, always. So like when you give an answer of like 27 meters per second, that's just a magnitude.
Oh, we
If
know.
you say east, west, or if you specify positive or negative, that's giving a direction then. Okay? Questions on this one? Can we move on? The next one's a lot more interesting. That's a basic one. Very small force, notice that? Very small force because it doesn't really take much to be, well, let's leave it at that, just a very small force. The next example we'll see about motion. Because this doesn't give us much about motion. Alright, this one I find really interesting because people see these X's and they wonder what is going on here. Now, we've been talking about into the page, out of the page, those terms. If I told you to think about that with regards to the X, what do you think the X might mean?
Sorry?
What do you think the X might refer to?
Where it hits
All those X's. Or what hits?
the force, the electron,
The
the beam.
proton. Field.
Think about into the page. If you, and this is a weird analogy, but it really works well. Take a bow and arrow, okay? Draw back your bow and arrow. Nobody? You fire an arrow. What do you see when you fire an arrow?
An arrow.
What do you see after it goes, though? What shape?
Dead person.
The dot.
Oh, you see the action.
What are the feathers, right? Aren't there 4 feathers always coming out the back of an arrow? If you fired an arrow and there were 4 feathers on the back of it, you would see like this wingtip. Or if you throw a dart, who plays darts?
Oh, yeah.
Yeah. Okay.
When you
this
throw a
makes
dart, maybe that's easier than an arrow. Throw a dart, don't you see the wingtips?
sense. Let me-
Okay? So what does this mean? This means that the magnetic field is into the page.
Oh, the little wing.
Okay? When you see the X, think about throwing a dart, think about into the page. That means the magnetic field B, see at the top here, B is labeled, is acting into the page. So your fingertips point into the page to start.
Orienting this line.
Okay?
That was 4 years.
Now, hold on. If there were circles instead of X's, it means the dart is coming at you. Think about the tip of a dart or an arrow. If an arrow is coming at you, you would see like a big, like the actual tip, right? Because it's rotating like that. So when the tip rotates fast enough of an arrow, seriously, you see like a blur, and it's a circle. So you would see a circle when an arrow was being shot at you. So if these were all dots, it means the magnetic field is out
That makes
of
sense.
the page. Now, if the magnetic field is into the page, everybody do this, please. Take your fingertips, point them into the page like this for a moment. Now, your thumb needs to point in the direction of the velocity. Well, the object is moving up, it's showing, tangential to the circle. So start with this. So it's pretty much like you're going to shake someone's hand. Okay, now, which way is your palm facing?
West.
Let's choose left. Left and right we'll choose for that. So left, right? Correct? So it's facing left. Now, if the force is pushing this particle left, it's going to move along a curved path, right? But watch what happens. Now which way is my palm facing? Kind of like at an angle, right? So it's going to keep moving me this way. When it's over here, which way is my palm facing?
Right.
So it's going to push it to the right. So no matter what, which way is my palm facing? The center of the circle.
It's not tangible.
Therefore,
It's not
Magnetic
tangible.
motion will be active towards.
what's going to happen?
It's gonna go in a circle forever.
Which is called what?
Centripetal force.
Motion.
There's a centripetal force, or it's moving in circular motion. Very good, Evan Reese. There is a centripetal force here existing from the magnetic field force, and as Ev said, it's going to move in circular motion. So, for these problems, remember how we always said, how does a race car stay around a track? Friction. Friction provides the the centripetal force. How does the moon orbit the Earth? Gravity. Gravity provides the centripetal force. So when a particle is moving through a particle accelerator, like the Hadron Collider, its centripetal force that's keeping it in circular motion is provided by the magnetic force, or the field really that gives it a magnetic force. Is that clear? This is the basic behind those high-speed trains, those particle accelerators, the quantum levitation video I put on News Forum. It's like one of the earlier ones. Has to do with very, very, very low resistance superconductors, but due to magnetic fields. Okay? So if that's true, take a look. What did we say when we solved this equation? What do you get when you solve this for F mag? BQV, right? That's what the magnetic force is. But didn't I just say that the magnetic force in this problem provides a centripetal force? And centripetal force from earlier in the year equals what? Yes, good guys. MV squared over R. Great. Come on, anybody contemplating the SAT subject test needs to have these memorized. Like automatic. So, if centripetal force equals mv squared over r, and the magnetic force equals bqv, but the magnetic force is the centripetal force, what am I going to do to these expressions? Set them, yes, equal to each other. Okay, set these two expressions equal to one another. As a result, what happens to one of the v's on both sides? Okay, one of the v's cancels out. And here's our equation. You do not need to memorize this. If an object is moving in circular motion, you will always set these equal. This comes about from conceptual knowledge, not memorization. Is that clear? If I tell you that the magnetic force is keeping an object in circular motion, boom, right away you start with this. You set them equal to each other. Okay, your tongue is blue. Like, really blue. You yawned just now. So let's keep this in mind. Next problem.
The BQ equals
Yep. BQ equals mv over r. A proton with a mass of 1.7 times 10 to the negative 27 kilograms is moving through a magnetic field with a strength of 2.5 Tesla. If the velocity is a very large number, 2.5 times 10 to the 7 meters per second, close to the speed of light, close to, okay, a high fraction of the speed of light, determine the radius of curvature of the path it follows. So if you know the speed and you know the field strength, and you know thank you, the mass, you can find the radius of curvature. You can find the radius of this experiment you're going to set up. Now, pause for a second. The object, the Hadron Collider itself, is built. And then what happens is the magnetic field strength is varied by varying the amount of electricity supplied or the amount of current running through it, like a voltage, okay? That's how you can vary the field strength. So the radius is really going to be a fixed number. You're not going to be trying to figure out what the radius is in real life. The radius is whatever the dimensions are of that super collider. The field strength B is what will be varied to get it up to different speeds, okay? So let's go ahead and figure this out. Why is it such a high speed, by the way?
Because it's a proton.
It's a proton, and a proton is a very small
Mass.
mass. If you provide a lot of energy and something has a very small mass, we know that right away, kinetic energy theory, right? If you have small mass, you have a really large amount of energy, velocity's got to be really high, okay? So let's list our givens. Our field strength is given. Our mass is given. Our velocity is given. So therefore, we need to find the radius. Q is also given. It's again a proton. If it were an electron, the tricky part is that this number becomes negative, right? But the velocity would really move in the opposite direction of a positive charge. So your velocity would probably have a negative sign to show the cancellation. But if it were an electron, okay, don't get bugged out if you get like a negative R for an answer. It's all that's meaning is it would move counterclockwise instead of clockwise. So it'd be like it would move moving this way. Okay, but I'll give you protons just to keep the answer to be positive. So solve for R. Solving algebraically, switch these two locations, remember? R equals mv over the product of bq. Remember in your calculator, put the product of the denominator in parentheses always. Because you're dividing by quantity. You're not dividing by b and then multiplying by q, which is what your calculator will do on its own. You need parentheses there. Go ahead and tell me what you get for R when you plug in the values given. You're going to get an answer in meters. I want you to then convert it to centimeters. We have not even 30 seconds left. The answer is, come on somebody, 0 point. Elliot or Scott? Sorry. I saw a hand, then I heard Scott. Which one? Point. Go, come on.
0.106.
That's it. That is it. So 10.6 centimeters as a radius. Thank you, Scott. Stay by the bell there. Perfect timing. Okay? So 1/10 of a meter. Tonight, make sure you practice 3 problems. Okay? 3 problems.